Hello again. Today we're going to discuss more about measurements, and in particular we're going to discuss something called scientific notation, and later on we'll talk about something called significant figures. So scientific notation provides a convenient way to express very large or very small numbers. And last time we talked about how in chemistry we tend to weigh really small amounts of material. So often we do end up with really small numbers. And when you have a really small number, so like the one at the bottom here, it can be really annoying to write out all of those zeros leading up to your actual measurement. So we can use something called scientific notation in order to simplify these values. So numbers written in scientific notation consist of a product of two parts. So this will be in the form of m times 10 to the n. So m is what we call a coefficient. And then 10 to the n is a power of 10. So m is going to be a number between 1 and 10, but not equal to 10. And then n is a positive or negative whole number. So down below we have a couple of examples of a really large number on the top here, and then a really small number on the bottom. And then on the right-hand side, we have the scientific notations for those values. So how do we go from the original number in standard notation to scientific notation? So what we're going to do is try to figure out what is our coefficient. So let's start with the larger number here. So I'm just going to erase these arrows, kind of clean it up a little bit, and I'm going to use a different marker color. So we're going to assume that there's a decimal point at the end of this large number. And we're going to say that that's the original position of our decimal point. Now, if m is supposed to be a number between 1 and 10, then we want the new position of the decimal point to be after the 1. So that is our standard position. And then we're just going to write out 1.001 as our coefficient. And then we have to figure out what is our power of 10. Or another way to think of this is how many times do we have to move the decimal point before we end up at the standard position? So let me just make some room here. So let's see, if we start at the original position of the decimal point, and we move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times, we get to the standard position. So that means that our value of n, or this exponent, is 10. Now, larger numbers have positive values of n. So now let's look at the smaller number on the bottom. So our decimal point is originally here, but if we want our coefficient to be between 1 and 10, but not equal to 10, then we need to move the decimal point over here between the 1 and the 0. So in this case, our coefficient is still 1.001. And we just have to figure out how many times we need to move that decimal point in order to get to the standard position. So we need to move it 1, 2, 3, 4, 5, 6, 7 times in order to get to the standard position for scientific notation. And you'll notice that the exponent here is -7. So smaller numbers have negative values of n. Okay, so we said that the standard position for a decimal is to the right of the first non-zero digit in the number m. So that's how we determine that coefficient value. But then additionally, we talked about how larger numbers have positive values of n, and smaller numbers have negative values of n. So another way to think of that is if you have a positive value of n, that tells us the number of places to the right of the standard position that the original decimal position is located. So that's kind of a confusing way of saying that the standard position is to the left of the original position. And then a negative value of n indicates the number of places to the left of the standard position that the original decimal position is located. And so what that means is the standard position is to the right of the original position. So whatever way works for you in terms of determining where the decimal originally is located, that's totally fine. Again, I like to think of it in terms of larger numbers versus smaller numbers. And I just remember it in terms of larger numbers have positive exponents, smaller numbers have negative exponents. So let's do some practice problems here. We're going to convert the following numbers into scientific notation. Now, if you would like to try this on your own first, you can pause the video, and then you can restart the video when you're ready to see the answers. Okay, so let's go over these values together. So for A, we have a smaller number, so it's 0.00401, and we want to write this in scientific notation. So first of all, let's figure out what our coefficient will be. And remember that we want to write this in terms of m times 10 to the n. And remember that m has to be a value between 1 and 10, but not equal to 10. So if we need a value between 1 and 10, then we probably want our decimal point to end up between the 4 and the 0 there. So this will be our standard position. So that means that our coefficient is 4.01. Now we have to figure out what is the exponent on our power of 10. So in order to move that decimal point from the original position to the standard position, we have to move it once, twice, 3 times. So our exponent will have a 3 in it, and now we need to determine, is it going to be a positive exponent or a negative exponent? So in this case, we had a small number, so that means that our exponent will be -3. Another way to think of it is that we had to move the decimal point over to the right, so that means that the value will be negative. So again, whatever way works for you for remembering how to determine the exponent is totally fine, as long as you get the same answer. Okay, Now for B, I'm going to use a different color so that we can avoid confusion. So in B, we have a larger number, 5,092. So we're going to imagine a decimal point at the end here. So we'll say that that is the original position. And again, we want to determine our coefficient, and it has to be between 1 and 10. So we're going to move that decimal over 1, 2, 3 times so that it's after the 5. So our coefficient is 5.092, and now we need to figure out our power of 10. So we had to move our decimal to the left 3 times. So that means that we do have a 3 in our exponent. And this is a larger number, so it would be a positive 3. So our final scientific notation is 5.092 times 10 to the third. All right, and now for the last example, I'll go back to the color blue here. We have another small value, 0.000078, and we need to figure out what our coefficient is. So if it has to be between 1 and 10, then we probably want to put our decimal between the 7 and the 8. So our coefficient is 7.8, and now we just need to figure out the power of 10 exponent. So in order to move the decimal point over to the right, we have to move it 1, 2, 3, 4, 5 times. So our exponent will have a 5 in it, and in terms of whether it's positive or negative, this is a small number, so it should be negative. Okay, so those are our scientific notation values. So for the first one, we had 4.01 times 10 to the negative 3. For B, we had 5.092 times 10 to the third. And for C, we had 7.8 times 10 to the negative fifth. Okay, so what if we wanted to go in the reverse direction? So let's focus on C here. And I'm just going to put a D down here. So we're going to convert to standard notation. Or you could also just think of this as a regular number. So let's say we were given 7.8 times 10 to the negative fifth. And you had to figure out how this would be written in decimal form. So what I would do is write 7 and 8. And then because this is a smaller number, which I know from the negative exponent, I'm going to start with my decimal point and then move it to the left because I know that this is a small number. So I'm going to move it once, twice, 3, 4, 5. And then wherever I have an empty spot, I'm going to put a 0. And these will be kind of considered placeholder zeros. And so that tells me that my decimal form looks like this. So I hope that helps a little bit with scientific notation and how to go between these two different forms. And here is the solution slide if you want to go over these later. So now, how do we use scientific notation in calculations? Because often in chemistry, we do have to perform calculations, and we should use scientific notation in certain instances. So again, if we have larger numbers or smaller numbers. So let's say that we're multiplying two numbers together. So down below I have two example values. So we've got a times 10 to the y and b times 10 to the z. Now what we're going to do is multiply the m values, or the coefficients, together. So a and b are going to be multiplied. And then the powers of 10, we're going to take their exponents and add them together. So the exponents in this example are y and z, and when we multiply, we're going to add those exponents together. Now, as an example problem, down below, let's say that we're multiplying 3 times 10 to the 8th by 4 times 10 to the negative 2. So again, we're going to multiply the coefficients together. So 3 times 4. And then we're going to add the exponents. So 8 plus negative 2 for the power of 10. Now, initially, what we end up with is 12 for our coefficient, and then we end up with 6 as our exponent, but this is not correct scientific notation. You'll notice that the coefficient is not correct. It is not between 1 and 10. So what we have to do, let's say we have a decimal point there after the 12, we have to move that over one space in order to give us the correct coefficient, which is 1.2. But when we move that coefficient to the left, that means that we have a larger number. Or I guess you could say that we need to add an exponent to the power of 10. So for instance, if we wrote out 12 times 10 to the 6th, so initially we just have 12, and this is a larger number, so we're going to move our decimal once, twice, 3, 4, 5, 6. And then we want to figure out the correct scientific notation. So this would be 12 million as our value. We're then going to, let me just erase these little marks here. We're then going to take our decimal at the end of this huge number and move it over 1, 2, 3, 4, 5, 6, 7 times. So that's going to give us our final answer of 1.2 times 10 to the 7th. Okay, so now what do we do if we're dividing two numbers using scientific notation? So let's say again we have a times 10 to the y, and then b times 10 to the z, but this time we're dividing those values. We're going to divide a and b by each other, and then multiply that by our power of 10, but instead of adding the exponents, we're going to subtract the bottom exponent, so the exponent in the denominator, from the exponent in the numerator. So as an example, let's look at the same numbers from before, but this time we're dividing them. We have 3 times 10 to the 8th divided by 4 times 10 to the negative 2. So we're going to divide 3 by 4, and then we're going to multiply that by our power of 10, where we're subtracting negative 2 from 8. So remember, if you're subtracting a negative, that actually becomes an addition problem. So this would become 8 plus 2. So in the final answer here, we actually have an error again. So our coefficient comes out to 0.75, which is not between 1 and 10. So we need to move our decimal point to the right one space, which means we're going to subtract 1 from our coefficient, from our exponent. So then 10 is going to become 9 at the end. And you could also write out this value and figure out your correct scientific notation, but just a couple of rules. If we go back, moving the decimal to the left means that you're going to add to exponent. So 6 becomes 7 in the exponent there. And then in this example, moving the decimal to the right means that we subtract from the exponent. So 10 became 9. So just a couple of rules there that can be helpful. But we always want to make sure that our coefficient is between 1 and 10, and sometimes that means adjusting the power of 10 as well. Now, the next topic that we're going to discuss is significant figures. So when we are performing measurements and recording data, we do want to make sure that we are representing the certainty of the measurement. And then using significant figures, we can represent the certainty. Plus, we're also going to add one number that is representing an estimated number. So significant figures really tell us which values are important in a measurement and which values are unimportant or insignificant. So we have a couple of examples here. We've got a ruler that we're using to measure the square up above. So let's try to measure that square. Now, this first ruler is not the best. We only have a couple of markings there. So we'll do our best, but we know for sure that that square is greater than 1. So we can for sure say that the side of the square is 1. And maybe this is in centimeters. So that value is significant, but then we also need to add an estimated digit. So let's see, let's kind of line this up here. So let's say that that's about 1.8 centimeters. So again, that last digit is an estimated digit, and all of your measurements should have an estimated digit present. Okay, now what about on the right? On the right-hand side, we have a much better ruler. There's more divisions present, so we can make a better educated guess about the length of this side of the square. Okay, so in this case, I'm just going to draw a little line here. We know for sure that this is 1.8 centimeters, let's say. But then we're going to add a little estimation there. So it kind of looks like it's in between 1.8 and 1.9. So I'm going to add a estimated digit of 5 there. So on the left-hand side, we were only able to get to a value of 1.8 centimeters, which isn't very accurate. But on the right-hand side, we had a much better measuring device. So we could say that the length of the square was 1.85 centimeters, which is probably more accurate. So on the left-hand side, that value of 1.8 tells us that we have two significant figures. And I'm going to abbreviate that as sig figs. And then on the right-hand side, we have three significant figures. So on the left, we're not as certain about our measurement, but on the right, we are more certain about our measurement. Now, sometimes in measurements, we have zeros, and zeros can be a little bit tricky in terms of being significant or insignificant. So down below, we have some rules for determining whether zeros are significant or insignificant. So leading zeros, which can also be considered placeholders, those are never significant. So down below, we have this very, very small number, and these leading zeros at the front, they're just used to represent how small the number is. So we would probably want to write this in scientific notation instead, because that would get rid of those leading zeros and we wouldn't have to deal with them. So again, leading zeros are not significant. Now, if you have buried zeros, or zeros that are in between non-zero digits, those are significant because they are between numbers. And then trailing zeros are usually significant. So these zeros typically show up after a decimal and after a non-zero digit. So I'm going to put above the leading zeros that these are not significant. And then buried zeros are significant. And then trailing zeros, it depends. Okay. So let's do a couple of practice problems to determine significant figures. And if you want to pause the video and try this problem on your own first, you can. So let's go over the first one. In A, we have 4,097 as our value, or our measurement. And we want to determine how many significant figures are in this number. So we have three values that are not zero. So those are all significant. And then this zero is in between non-zero digits, so it's a buried zero, which means that it is significant as well. So all digits are significant. So that means that we have 4 sig figs, which I'll abbreviate as SF. Okay, now in B, we have a small number, 0.002803, and we need to figure out which digits are significant. So we know for sure that the 2, the 8, and the 3 are significant because they're non-zero digits. But then we have to figure out, are the zeros significant? So we have these 3 zeros at the beginning of the number, and because they're at the beginning, those are called leading zeros. And remember that leading zeros are not significant. And then we have this 0 in between the 8 and the 3, And that 0 is a buried 0, so it is significant. So the 2, 8, 0, and 3 are significant. So we have 4 sig figs. And then the last one is really tricky. So here we have a 3 followed by 2 zeros. And we know the 3 is significant because it's not 0. But then those 2 zeros, we would call those trailing zeros. And in this particular instance, they're actually not significant. So in this case, we only have 1 sig fig. But let's say that this was written as 300 with a decimal point at the end. That decimal point tells us that we are sure of those 2 zeros. Whereas before, without the decimal place, we weren't quite sure if those zeros were significant or not, or if they were just placeholder zeros. So adding that decimal point tells us that the zeros are significant and that we are certain of our measurement. So in that case, we would have 3 sig figs. So sometimes trailing zeros are significant, sometimes they aren't significant. So in general, if these come after a decimal and a non-zero digit, they are significant. So I'll put at the top significant if after a decimal and non-zero digit. Okay, now there are, some tricky numbers here that we went over, but hopefully this helps a little bit with significant figures. Now, one thing to keep in mind is that scientific notation, which we just covered earlier, will always tell you the number of significant figures. So, for example, let's look at the first value, 4097. We would write this in scientific notation as 4.097 times 10 to the third, because we would have to move the decimal place 3 times in order to get to our coefficient. And this is a larger number, so the exponent would be positive. And the coefficient tells us the number of significant figures. So the coefficient in scientific notation tells us the certainty of our measurement. Now if we look at B, we would write this in scientific notation as 2.803 times 10 to the negative third. And, the coefficient tells us that we have 4 sig figs. And in scientific notation, we don't have to use those placeholder zeros that were distracting us before. So scientific notation is really useful not only for recording large numbers and small numbers, but also for telling us how certain we are of our measurement. Okay, and then this is the solution slide if you want to go over these later. So how do we handle significant figures in calculations? We often have to keep track of how many values we're certain of during a calculation. So what if we're performing a multiplication problem or a division problem? there's going to be different rules than we would have for addition and subtraction. So if you are multiplying or dividing numbers, then the answer must contain the same number of significant figures as the quantity with the fewest number of significant figures used in the calculation. So let's look at a couple of examples. In the first example, we're multiplying 4.325 by 4.5. So maybe we're determining the area of a square, and the length of one side is 4.5, the length of another side is 4.325. So I guess this would be a rectangle instead. And let's just draw a little picture so we can kind of visualize what's going on here. And I don't know, maybe our unit is centimeters. I guess it doesn't matter here. Now, in the first value, we are pretty certain about the length of that side. We measured it to be 4.325. So that's pretty detailed. But then our other value is only 4.5. So we're not too certain of that value. And our answer has to reflect the certainty of our measurements. Or in multiplication and division, the answer has to reflect the least accurate measurement, because we can't be more accurate than our least accurate measurement. So the first value has 4 significant figures. The second value only has 2 significant figures. So that means our final answer also has to have 2 significant figures. Now, when you plug this into your calculator, you're probably going to get a very long answer. So in this case, 19.4625. So you're going to have to simplify this and pare it down to just those first 2 significant figures. So our answer would end up being just 19. Now, if we're dividing those 2 values, so let's say we're dividing 4.325 by 4.5, our calculator is going to give us 0.961111. And because our least accurate measurement only has 2 sig figs, that means our answer should also have 2 sig figs. And remember that the 0 here is a leading 0, so it is not significant. So we're really only counting the 9 and the 6. Now, what if we're adding or subtracting? The rules are a little bit different here. So the answer obtained by addition or subtraction must contain the same number of places to the right of the decimal as the quantity in the calculation with the fewest number of places to the right of the decimal. And we're going to abbreviate that as PRD. So let's look at an example of an addition problem. And let's say we're adding 5.325 and 5.5. Again, when you're adding or subtracting, we really only care about the decimal places. So in this first value, we have 3 decimal places, or places to the right of the decimal. And in the second value, we only have 1. Now, when we plug this into our calculator, we're going to get a pretty long answer of 10.825. But we have to make sure that this is representative of the least accurate measurement. So we're going to limit this to 1 decimal place. So our final answer is 10.8. And the same thing goes for subtraction. If we were subtracting these numbers instead of adding them, we still want to limit our answer to 1 decimal place. So our calculator is going to give us negative 0.175, but we have to limit ourselves to that first decimal place. And something that we're going to talk about next is rounding. So just as a brief preview, because the next decimal place is greater than 5, we're going to round up to 0.2. Okay, so let's do a couple of practice problems with significant figures. So for A, we're multiplying two values together. For B, we're adding two values together. And for C, we're dividing two values together. So if you would like to pause the video and try these on your own, you can. And make sure that your answer reflects the correct number of significant figures. Okay, so let's go over A together. So in this problem, we're multiplying 0.0420 by 55.98. And when you plug this into your calculator, you probably get a very long answer of 2.35116. However, let's figure out how many significant figures are in both of these values since we are multiplying. So in the first value, remember that we don't count leading zeros, so those are not significant. But the 4 and the 2 are significant. And then this 0 here comes after a non-zero digit and a decimal place, so it is also significant. So that means that we have 3 sig figs for that first value. And then our second value, super easy, nothing is 0, so all of those values are significant. So that is a total of 4 sig figs. So because our least accurate measurement has 3 sig figs, that means that our final answer will also only have 3 sig figs. So it would be 2.35. Now for B. In this case, we're adding two numbers together, so the rules here are a little bit different. We're going to be more concerned with the number of decimal places. So in our first value, we have 1 decimal place, or 1 place to the right of the decimal, 1 PRD. And then in the second number, we have 3 decimal places, so 3 PRD. And when we plug this into our calculator, we get a long answer of 958.932. And we want to make sure that this answer reflects our least accurate measurement, or least certain measurement. And so we want to limit ourselves to 1 decimal place. So our final answer is 958.9. And then in C, we're dividing two values. So we're dividing 30.2 by 23. And because we're dividing these two values, we're going to look at the number of significant figures. So our first value, we have a 3, a 0, and a 2. And that 0 is a buried 0. So that means it is significant. So we have 3 sig figs. And then in our second value, we don't have any zeros there. So both of those values are significant. So we have 2 sig figs. And then our calculator gives us a super long value. So I'm just going to write out a few digits here. And again, we want this answer to reflect the least number of sig figs, so we're going to keep this value at 1.3, so that we only have 2 sig figs. Okay. And here's the answer slide if you want to go over these answers later. And the last thing we're going to cover today are rounding rules for numbers. You might have learned this before in previous math courses, but just as a quick reminder, if the first of the non-significant figures to be dropped from an answer is 5 or greater, then all of the non-significant figures are dropped, and the last remaining significant figure is going to increase by 1. Now, if the first of the non-significant figures to be dropped from an answer is less than 5, then all non-significant figures are dropped and the last remaining significant figure is left unchanged. So, for example, let's say that we had an answer of 10.825, and we know that we have to limit this to 1 decimal place. Then we're going to chop off the 2 and the 5, and the 2 is immediately to the right of the 8, and because it's less than 5, that means that we don't have to do anything to the 8. The 8 is going to be left unchanged, so we end up with 10.8. But if we need to round negative 0.175, which was our answer from a previous problem, and let's say we're rounding it to 1 decimal place, so we're chopping off the 7 and the 5. The 7 is immediately to the right of the 1, and it is greater than 5, so that means we have to add to that 0.1. So it's going to end up as negative 0.2. Okay, so I think that's enough for today. This video was a little bit longer than our previous videos. If you have any questions, please feel free to email me or schedule an office hour, and I will see you in the next video.